1, 2. Morning? Oh. Good morning. I'm the last session before lunch, the best. Are you all hungry or? Yeah, well, not hungry for knowledge. I'm Gregory, as probably my accent betrays, I'm French. I just do my first conference in 4 years, so the stress is very high. Thank you for being, a kind of a good audience. I wanted to share with you about 10 years of research that we've been doing with our company and trying to kind of give you some hints about how you could do some of these things yourself and what you shouldn't do. And I'd like to have a very open discussion on kind of what is your experience and so on. So if you want to interrupt me and just like raise your hand, there is a microphone that is going to kind of fly around. But the objective is really to have a conversation and kind of some of the things we've done. So one of the original problem that kind of I've seen is back 10 years ago, I was in one of the social network companies that you're using on a daily basis. And they've been hacked. Their user database has been hacked. It's actually not publicly known. And they came to kind of me during the kind of one of the meeting and say, hey, what about you will be able to detect these type of things, because they were, at the time I was working for a Wi-Fi company. I was like, what about you would be able to detect this kind of malicious behavior? And I'm like, well, that's very interesting, right? Let's kind of, back 10 years ago, like how would we be able to do that, right? So it was an APT group. It was trying to get some kind of proper intelligence about kind of the user of that network. And so we did some fundamental research of this, and that's what I want to share with you. Okay? So the first thing first really is, if you look at the landscape that exists today, there is a lot of frameworks. I don't know, have you, I expect that some of you are hackers here, so who is using at least one of these frameworks on some regular basis? Here you go. That's pretty cool. What is interesting, right, if you look at all of these things, some people believe that they can be in there, you can know them, and still they will be able to evade your defense. Funny enough, right, if you look if you look for kind of a Cobalt Strike, it's used by the Chinese government, for example, for very kind of obvious, offensive attacks to different critical parts of the infrastructure of Europe. It's very clear, everybody knows it. We know that it's a release that of Cobalt Strike that has been linked back 2 years ago in April. We know exactly what is the release version, yet we are not able to find it. So how is that, right? You know the tool, you know the payloads, you know how the payloads are being built. You're still not able to find it. That is insane. So the real reason here is because of the different evasion techniques that exist today, right? I don't know if some of you have been ever going to a website like iread.team. It's like you take the most stupid person that you can find, like me, and just like say, hey, become a hacker. And then they tell you, you run that command and you modify these 2 bytes of information, and then Microsoft Defender is bypassed. Like, it cannot be. Then you try, and then it works, and that's worrying. The reality is, if you look at kind of the threat intel as of last year, the best threat intel report that I found was one from Recorded Future that aggregates multiple threat intel from many different sources. They identified more than 10,000 command and control servers that were active in 2021. And they knew that after the breach, right? So it's kind of a consolidated set of tools. What is interesting is, if you look at the breakdown of the attacks, it's like a third of them, actually 26% of them, is Cobalt Strike. Still, it runs and is undetected by the people that are owned. And they learned after the fact. But whenever you look into the breakdown of the list that you have behind me, you will see that all of these tools that we know and all of this post-exploitation framework we know, the numbers don't add up. You still know that there is some node bad. You still know that there is some command and control. And in more than half of the cases, you're not able to understand actually what the tool used. And the reality is, most of the time, it's Cobalt Strike, most of the time it's Metasploit, most of the time it's this tool. So then the reason, like, and I come up with some sort of, evasion techniques and so on that exist in the wild to kind of be able to understand that. But the most fundamental reason why it's not detected is because Cobalt Strike can overcome with this notion of malleable profile. So standard IDS, IPS tools are never going to be able to find these payloads. And because of different EDR obfuscation techniques, most of the time, they would not be found either. So that's kind of an example of the level of customization. I'm engaged, on average, every 2 to 3 days into some sort of incident response engagement for the last 6 years. And I'd like to show you an attack that is brand new and fresh from one of an organization that I kind of helped last week on kind of doing some sort of early detection. And I want to give you a bit of my perspective on what happened and not in there, and just go through the sequence of the attack. What I found absolutely interesting there is after 11 minutes, the infrastructure was completely on and Active Directory was broken. You think it's a 10,000 IP address infrastructure, so a pretty substantial organization with more than 5,000 employees. After 16 minutes, the redundant Active Directory infrastructure was owned as well. So let me give you a little bit of a breakdown of this, because I believe it's interesting. And the other thing that I want you to take away of this conversation is actually my talk is completely useless. Command and control alone means nothing. Finding the command and control gives you an entry point of where to look at, but you need to think about the complete attack chain and find the path of the hack to be able to really kind of have a good performing incident response kind of engagement. Funny enough, right? So the attack group that is in there, we haven't qualified it. It might be 5 ends. We're not too sure. But what is interesting, right? If I look at the engagement, it's like, some very weird port scan coming out from the outside, which is rare because most of the time it will be email phishing. 95% of the time it's the case. And the second thing is like, hey, first command and control on one of the servers that actually is the DMZ. And don't ask me why. The guy is just didn't really think that, DMZ to Active Directory should be blocked somehow, and they opened the door. Or never close it after they did some interventions. Really some crazy things. So what happened is they infected a first server in the DMZ, and then from there figured out to kind of pivot into the data center by doing some very simple reconnaissance. And what is interesting is there are different the kind of detection opportunities. And I heard the previous talk, and one of the last question was, yeah, what about you brute force the account? Whenever you find the account, then what do you do? Well, just to be clear, nobody never brute force anything with an intent of brute forcing anything. There is always a greater goal. As a hacker, whenever you get somewhere, you're there, you're kind of blindfolded, and then you kind of try to figure out what is the landscape around you like. So whenever you're going to have some sort of local account dump, think about any sort of technique that you can imagine. The next thing is there is going to be an attempt to reuse these accounts somewhere. Most of the time, you will need to kind of pivot inside of the network to be able to get this thing. And there is multiple opportunities for detections outside of the command and control. And most of the time, there is very large abuse of RDP, RPC inside of the network to kind of laterally progress. So to complete a bit the question that was before about, hey, what happened whenever there is kind of a local brute force? The answer is, well, nothing really on the network, but how this account is going to be leveraged is a very interesting detection point for anyone in this room. The next thing is really, I start to see as a trend less and less type of forward scans and so on. And instead of that, I start to see more and more RPC, RDP, kind of high-level protocol use and kind of living out of line type of attacks. And it's interesting because I remember back 3-4 years ago, it's exactly the way APT groups were working. And if you look at the behavior of what we see from APT groups from like 3-4 years ago compared to how ransomware operators hack today, it's exactly the same. There is a slight delay of knowledge, and it's very obvious. But we see them learning this kind of different technique coming from governments and reapplying these techniques to kind of apply, in an efficient manner, their ransomware attack. And that leads people to be able to be Active Directory, domain admin and kind of own more or less every single bit of the network in less than 16 minutes in that case. But what is interesting, right, is whenever what you see here, the set of applications and so on that are kind of being used like Cobalt Strike, almost vanilla, just some sort of manual profile that were changed, and kind of going back and just making some sort of like privilege escalation. But what is interesting again is the EDR just added one of two few signals that were detected about, oh, there is probably something weird. The reality is, and there is EDR coverage in every single of these endpoint system. And for not offending the vendor, it's one of the top 3 vendors that exist on the critical thing on the Gartner Magic Quadrant. And it's a very good EDR. But hackers have become much, much better now at finding techniques and document these techniques. If you look at the Conti ransomware group chat, they actually have very clear documented steps for every single EDR that exists in the market to bypass this. So that's something to take into consideration. So we expect that kind of if we were not to kind of act on this, in less than 2 hours, the whole infrastructure have been crypto-locked. Where I'm going with that is it was very interesting to be able to find this kind of command and control activity because it was the entry point for the attack. And I'm going to go deep dive into now what we have seen in that specific example and what we see in general and the different techniques that you can apply. So the first thing first is there is a belief that if you're able to see what is inside of the traffic, inside of the SSL layer, you will be able to find a ransomware, you will find your hackers and so on. That doesn't exist. Just I want to be very clear, and I've got a bit of a very weird screenshot on what we see inside of an HTTPS tunnel, inside of an organization. Depending on who you are facing, right? If you're facing an APT group or whatever, you're going to have encryption layers within the SSL layer itself. We see hackers doing that today. We see hackers leveraging tools like Bug, Dropbox, Twitter, and so on to push some image and doing some sort of comments forwarding through Twitter images posting, right? There is very creative ways to evade today existing systems, right? And there is no white kind of list and so on that will ever be able to allow and or prevent these type of attacks. But what is interesting, what is really core is like, okay, let's figure out about how we will kind of find these activities no matter what. The second set of problems that I kind of observed, right? If you were to think about, okay, behavior of tools like Metasploit, Cobalt Strike, Portion Empires, and so on, have one thing in common: they beacon out. So what they will intend to do is kind of, hey, I'm going to connect to whatever my command and control server. But the reality is, if you were to look in every single machine, every single phone, every single piece of the infrastructure that kind of beacon out, you're going to see that there is a lot, right? On average, we see a beacon activity in every kind of almost 2/3 of the machine inside of a network. There is always something that beacon out at least at the rhythm of 5 minutes in every single machine that exists in that room. So relying on finding these kind of beacons like some traffic going out is not probably a very good strategy, but at the same time, you need to have your update system running. You still have to need to run antivirus that have the update of signatures. You still have to do all of these things to kind of run. The second is, as these kind of ransomware groups, like last year they made $2.8 billion of billing to their kind of customers, right? They kind of start to really make a lot of money. Because of that, they're able to make some very complex infrastructures, and they have the kind of money that allows them to do that, which means that the infected client that might happen in the network is going to kind of go through multiple kind of proxies and relays in order to go to the backend infrastructure and eventually to kind of allow to interact with the hacker. That's the second thing to consider. It's not like you beacon out to one server. You will beacon to kind of a round-robin of servers. So how do you find that? And just to, I want to reiterate on that. So that is a characteristic of an infected machine at moment zero, starting to kind of have some sort of interaction with a command and control server over an SSL layer. My very poor screenshot is trying to tell is inside of even the HTTP header that you will get out of it, you're going to see that, and that traffic was decrypted, on the fly for kind of testing purposes. what you see here is inside of the HTTP wrapper itself, you've got kind of ciphered command. So the content of the HTML page is inside of an object that is ciphered, so you're actually not able to understand that there is actually something going wrong. Is it through kind of a JavaScript obfuscated code? Is it through an image that has been applied some sort of cryptography around that? It's going to be very difficult. And also it's most of the time protected by one unique key that is proper to an engagement, so you're not able to decipher that either. I was taking the example of APT29 because it's exactly what they do. So let's try to find then kind of different ways to be able to address that problem then, I am a firm believer, probably because I've been seeing that very successfully running since many, many years, that you need to think about very specific set of problems solving different set of kind of tunnel that exists. There is actually 3 ways to do tunneling today. No more than that. If you think about all of the tools and all of the kind of Cobalt Strike and Merlin and Covenant type of things that exist in the market, they actually have 3 kind of network behaviors only. And these behaviors is really like the simple things like I kind of ask for my next command and I get the return and I apply that locally and I send the bulk of data out. And in the way the behavior is on the kind of the lower TCP level, it's actually pretty characteristic. There is just 3 ways to actually represent that. I'm going to go into the detail of what it means and how this traffic is in detail in the next slide. But then the question is like, how do I efficiently, I'm able to process this data? You think about every single bit of traffic going out of your network, that can be multiple megabyte, gigabyte of traffic per minutes, days, hours, depending on the size of your environment. So how do you find an efficient way to process through multiple set of algorithms that very specific set of problems that you have, which is find the command and control channel? We have inside of our team people that are pretty clever and that have all PhDs into data science. And inside of their tool sets, what they have is like, okay, I've got so many cool tools that I've learned, so more or less there is nobody in the world that really does AI applied to cyber kind of threats. So they are like biologists and people like working ex-NASA people and this type of organizations. So we like say, hey, you should do that for cyber. All the stuff you learn in machine learning and so on, you could apply for cyber. And so we get this guy and they come with this tool set of different algorithms that they could apply to specific set of problems. The problem for kind of any sort of data science problem is the CPU time that is available. And how are you going to be efficiently able to run that? Think about this ginormous type of data set that you can have. Yeah, if you have unlimited CPU, you probably will find the bad guy, deep neural networks, get the problem sorted. You will probably find something. You cannot apply that with this type of data set at speed. And whenever you think about these 16 minutes to kind of be kind of at the data center and kind of at the DC level and have kind of an Active Directory announced column, it's like how within the next kind of 2, 3, 4, 5, 6 minutes, how am I able to detect that and provide a signal that is meaningful? So you cannot wait for a batch of data to run in kind of a day or every hour even, because an hour later you're gone. So that's a set of problems, and as we went into the different iteration of kind of our research, we started with like, hey, let's try to kind of figure out what is artificial intelligence, which is try to be kind of mimic the human mind. And then we started to see like, okay, we are going to try to figure out what is the norm. We had these great ideas like, I'm going to look what is the norm in the network, what is the baseline of every communication, and maybe there is something that is out of the ordinary. It's like, hey, if your command and control channel is Twitter, good luck at finding the anomaly. It doesn't exist. You got to think as well that because of adwares and kind of all of this kind of ad campaign tool that exists, an average user goes for more than 10,000 websites without knowing it in the same day. And they will visit most of them once. So you cannot base your thing on anomaly. So it's like, okay, so maybe there are kind of set of representation of data, groupings, and kind of analogy that I can start building. And then the most sophisticated thing is like, hey, maybe I can have some deep neural network models that would kind of be able to process data at speed and kind of very much like what Google does with their kind of voice system, able to understand that there is something wrong. The problem with that is there is always a bias based on the data set that you have. For example, back 5 years ago, the most common word for Google was chuk chuk. Do you know what a chuk chuk is? Nobody does. You know what? Because most of the data record they would get were from Android user phones that were saying, hey Google, or I don't know what is the hi Google. And there is that moment when Google kind of record the data and process it into their data center. And because so many people were actually nearby a train station, that chuk chuk was the noise of the train going off the rails. So you've got to think about this kind of bias of information that you cannot really trust neither the data science there, and you need to have always relearning of it. So that is kind of where we've been going through. And before meter attack and so on, the way we've been approaching the problem is like, okay, let's find the data set that actually we can rely on and avoid this chuk-chuk problem type of thing, right? So we took so you probably have heard about this Microsoft printer problem, right? When you could actually inject malicious drivers inside of every single Windows laptop from Windows 3.11 to Windows XP. So that's one of our researchers that found that stuff. And we took these very high-level, super clever guys and said, hack the world. Show us how you do. Show us how different governments have been teaching you to hack. And then based on that, we've been able to build a certain set of data set of what would be the bad. And then we're like, okay, you're probably very good at hacking and probably very clever people, but the data same thing is a different set of problem. So what about then we figure out how to extract the relevant piece of data outside of the infrastructure of the data of the network and say, I'm going to work on an online of theory of what could be the data set. So for example, think about the command and control channel. You will have the elliptic curve of the certificates, you will have the TCP connections, the length of it, the size of the packet, the size of the communication, the speed of it, the RX, the TX, and maybe there is something that we can extract out of it. So out of this theory, what we did is like, okay, let's get a few customers and let's prove our theory. And then based on data set of millions of objects, we've been able to build and rebuild our model, improve their training, and publish always better algorithms. So more or less what it means is whenever you think of data science problem and finding this of command and control tunnel, the key is being able to get enough bad to understand how the bad behave, and then be able to extract the common feature from an algorithm perspective of what is relevant. And then it's like, okay, so that's the problem, that's how we are going to work. Then the question is like, what is our process and our thought process and what we went through? The first is like, hey, we probably can find some sort of IOCs, right? Some kind of known bad. Yeah, but when it's known bad, it's too late. So that doesn't really work. So let's try to figure out, okay, this IOC probably could contribute for enrichment, but nothing more than that, maybe for some of additional intel. This what is unusual instead of HTTPS connections, for example, because we know that most of the communication is HTTPS inside of this communication framework. The reality is, it's an absolute nightmare. If you look at the tree of discovery of what a website does and the number of interfaces with all the websites that they query, you end up not being able to really have one specific type of alert, and you end up with a lot of false positives. And do you really want to spend your life just triaging false positives? Probably not. Right? I mean, I work with some network which are like 200,000 IP addresses and more. You don't want to have 200,000 alerts per day, right? You probably want to have one. So the second thing is like, okay, let's figure out if there were a way to extract the XSL metadata eventually or the TLS metadata and figure out if there is some rare destinations. But again, the problem we had before is like, yeah, but what about you have multiple proxy servers that are relaying the communication to the readback infrastructure? They actually might have very different domain names. So we need to figure that out. So it was a little bit better, but it was not that. So what we ended up is like having a model that says, actually a couple of models that says, let's figure out all of the beaconing activity because it's what is common with all of these kind of frameworks.
saying there is a communication back to a system. And the encryption technique and the way the HTTPS kind of certificate is being created is always the same because it's sourced by the same tool. So every single proxy and relay communication will have the same way to create the certificate, even if they have different names. So let's take that as an input layer. Let's take eventually like the HTTPS communication and the ES3 property of the traffic itself. Let's try to figure out as well the pace of communication of each of these tunnels. And when we ended up kind of finding as part of research, is like a baseline of communication is you ask for a website, you get kind of data. And there is a very kind of clear kind of, you actually ask probably 1/8 less, actually 1/8 of the data is what you ask and kind of the rest is what you receive in a normal traffic and communication. Except if you have some sort of weird updates and stuff like that, but it's very likely that it's going to be like that. If you look at a malicious connection, you're going to have a pattern which is more or less my command and control baseline here, going back to my server, and there is the moment when you're going to receive a command and say, you should probably do that on that machine. That is going to locally run on the machine, and then then the machine is going to send back, usually at the next ping or a few moments later, send back the data and say, that's what you've been looking for. And that pace of communication is what we end up doing today as kind of the means for us to be the most efficient at finding attacks and command and control servers. And whenever you think about it, it's like you could expand on that in any sort of kind of IP communication. You don't have to have it SSL, right? If you think of it a remote shell, a reverse shell, what will happen is you have some sort of communication that are running, and then you're going with your mouse and keyboard to answer remotely some kind of data, which is going to be the burst that you see here. And there is going to be a common execution. So your Metapreter shell and whatever is going to have exactly the same behavior. So that's the, so infected response, attacker commands. But that's the principles, right? And then the way we do that, right? So we have been able actually to label more than 100,000 kind of malicious command and control tunnels with active communication of hackers. And based on that, we've been applying deep learning. The actual mechanism is short-term memory loss. It's LTS and short-term long memory loss algorithm, which is the same the library that you get by default with TensorFlow, allowing you to kind of do these things. So it's the same kind of library that Google uses for speech recognition. And as an input layer, as I said, you got all of the certificate information, the activity curve, the communication, the TCP timing, and so on. And in real time, the neural network is able to get a fingerprint of the normal communication. Very much like you, whenever you see a bird, you know it's a bird because it looks like it got two kind of wings, 2 feet, and probably it flies. That is sufficient parameters to identify a bird. And funny enough, sometimes it's a plane. But most of the time it's a bird, right? So the thing is like, how do we kind of refine that, and how do we have better data set to kind of remove the plane type of problem out of the bird type of data set you want to find? That's what we've been doing. Just to give you an idea over the last 5 years of research about what it means, right? Getting to that level of understanding and kind of give you the summary of what I just presented actually is a bit of effort. If you think about it, like we had roughly, I think it was something like, that's the man years or the man months that we kind of required to be able to kind of process. It's more or less 4 years of constant work of a team of 2 or 4. And it was like real-time people that were just hacking, getting data samples, comparing with kind of real-life data from our customers, improving and so on. This year, our investment has been 6 people a year so far to improve that. So think about 2 hackers full-time plus 4 data scientists, PhDs full-time to do this type of effort. The amount of work that is required to do that and to this teaching is extremely complicated. So complicated that we managed to kind of patent it because this research is unique. But the way you want to kind of, the way I want to kind of get out of this conversation is like, you're going to build your own experience yourself as, as companies about what are the potential attacks. Go document, learn, get as much data as you can, figure out a detection strategy that allows you to find the known bad, because if you look at even last year, most of the things that even you know is bad, you don't know about them. Out of these 10,000 command and control infrastructure, there are still more than 5,000 where you just have no idea who they are and what is kind of the tool behind. So that would be one. And then I really wanted to open for question and answers and take a little bit more time to make sure that, first of all, I was clear, which is not always the case because I'm very passionate and I speak sometimes very fast. But also, I wanted to make sure that it was clear. So I hope it was informative. It gives you some sort of ideas. I'm more happy to kind of speak to you, kind of have a discussion over lunch. I'm at the booth down there, so just, pop by. We'd love to talk about it. There is my favorite cheerleader that behind says, by the way, if you pop by the booth, you get headsets. There is going to be kind of a lottery type of thing, so just, come and participate. Thank you.
Thank you, Gregory. I could almost hear my hairs falling down. It was completely silent in the room. Are there any questions from the audience?
Yes.
Okay, just a minute. I walk with the mic. Or if you can please approach so we don't get the feedback.
Or please come on stage with me. I will feel less lonely. It's a trap.
Can you hear me? Yeah.
Hello?
Yeah, so my question is, how do you deal with false positives? Because this is an important problem, right? You can have an accuracy of 90%, but also false positive rate of 8-9%, which is bad. But you can also have 85% accuracy, but a lower false positive rate. So how do you deal with that?
There are two ways. So the way we solve the problem is because we have constant relearning, and we republish the learning. If you were to build your own model and do these type of things yourself, the answer is you will have to kind of look at the algorithm fitness, and then there are some techniques that exist to be able to do that. From a tooling perspective, right, there is always ways, no matter how you can kind of consume your detections and alerts, kind of triage out the roles. My observation is most of the time, what is kind of perceived as command and control are usually command and control. Like think about somebody that is taking ownership of your laptop, an IT team taking remote support of your machine. They would probably go through Teams or Zoom or whatever is the tool of choice, and they're going to start doing some sort of control. And then there is probably a few systems you want to blacklist, saying, well, that is expected that Zoom is used, for example, for remote access in certain cases for certain users. So you probably have to nullify that. What is really difficult from an AI perspective, right, if whenever you have a good way to detect command and control activities, you want to be able to see all of them and then say, well, there are some whitelisted maybe applications. So if you were to build your own, I would say just kind of try to find the one that will have the best efficiency to find this kind of command and control, and then kind of newly find just whitelist or kind of triage out the data that will be kind of benign traffic for you. It actually is so we try to do it the other way around, kind of to train algorithms about what would be a good kind of command and control compared to a bad. From a traffic specification perspective, it's very difficult. So it's probably better to just say, and it should be probably 10, 15 applications in the network that should or should not do that. Like you have support from, I don't know, Pure Secure, Pure Storage, or you have maybe Dell or HP. They got their support system for managing their kind of cluster data center and so on. You will have to enable these and say, okay, it's fine. It's probably a safer bet from a detection perspective. I hope it solved the long answer for the short question.
Sorry for pulling you out, mate. If you want to avoid to be pulled out on the stage, just put a question in Slido. But anyway, if anyone has a question, just raise your hand. The lady again. I jumped out.
Thank you. How we can deal with the data imbalance issue while we are finding or detecting the attacks in ML and AI?
Can you expand a little bit?
Data imbalance issues. Like generally when the traffic is collected, all the time we don't have the attack traffic. Maximum time we have the benign traffic. So just for an example, if we have the 1 lakh traces, about 80,000 is benign traffic or only 20,000 would be the attack ones. So there is an imbalance issue in the data always. So how we can deal with that?
You got to create more true positive.
Oh.
I mean, the biggest problem we have ourselves is to get the real bad samples. If you don't get these real bad samples, don't even try. Like this was for us a really breakthrough in the last 4 years when we really had a much better qualitative true positive, because that's where the algorithm fitness drastically increased. So either you're able to create some, either you're able to get some through kind of third-party means. Trying to generate yourself is actually pretty difficult because you never really behave the way a hacker does. So you really, in the best possible way, if I were to kind of, give you a shortcut of 10 years of research, is try to find some people that give you some bad. So, I'm sorry.
Okay, thank you. Then we have a question on Slido. Is it a scalable solution or it could be applied for a different size of companies?
So machine learning as a whole is just a matter of how much RAM and CPU I'm able to throw into the problem, right? Depending on how you build your algorithm and the data and the efficiency that you're able to get, you're able to do a lot of amount of data processing. In our case, our largest size customer is 500,000 users, and it works. And the smallest user we have is 450 people. So anything in that range, we will eventually detect it.
Oh, thank you. Any questions from the audience?
And funny to the point, right? There is, if you were to look at kind of traditional IDS methods, even if you look at the improvement of the tool like ZPros, Suricata, and so on, doing pattern matching, string matching from the CPU and compute perspective is actually pretty difficult. It's actually very CPU intensive. Whenever you have your mathematical model and your neural network running on GPUs or kind of dedicated hardware or standard hardware but with optimized libraries and compilation, you actually are able to do much, much faster data processing that you would normally with pattern matching. So to complete a bit the question.
I might have some questions because I made the notes during your presentations. And one thing that I mentioned when you showed the timeline was that some of the EDR products could actually maybe detect only few activities, but not definitely all. And then it comes to my mind, as I mentioned before, there are some new types of malware that are using new TTPs. And if we take a look on the development, how these APT groups developed from like last 3 years, how does this affect your research when you look for the traffic to command and control servers? Is there any change in the behavior? Could you elaborate on this, please?
Yeah, like 3 years ago, we would not see these proxy servers really. What was interesting, if you look at, for example, kind of there is a very famous attack, right, called SolarWinds. Actually, what is funny with SolarWinds, right, is the server was created in 2018. The certificate was created 2 years prior to the attack. It was actually kind of hidden behind something that was fully legitimate. What we really see clearly is the attempt to hide yourself is actually much, much better today. So you will have kind of a proxy kind of website that looks roughly legitimate. We'll have, a lot, like the communication is massively hidden. And we see that more and more, and kind of it's thinking that there is kind of a bad website or bad communication is something we see less and less. So that is the big change that I kind of observed. So this kind of proxy communication. No matter what are the new techniques that exist, right? I will say you can nail down a few kind of progression behavior. always, no matter what. Like you have always like checkpoints that we see hacker performing network that they will never be able to work around. You need to steal the credentials, and you need to reuse credentials. And as much as possible, you try to live out of the land and use the tool that exists already in the machine. It's very rare that we see anything different today, and more advanced the attack is, less and less we see kind of tools being pushed on the machine. That is a big trend, and we see exactly the same behavior for IPT groups today. So that is the big change that we could see before. And also we went from a transition where you upload a malware that would be a big aggregate of many, many functions. And right now we see an implant. We see hackers kind of progressing, kind of building a map of the network and try to do as much damage as possible. The worst example that I had is a company which is a sort of clothing department, reseller, that has about 25,000 employees. The hacker was on site for like roughly 7 to 8 hours, and then started to do some fingerprinting about what is the backup system and so on. And what they did is they zeroed every single backup 30 minutes prior to the attack. Then they launched an attack. We informed the customer that something was wrong after 15 minutes, and so it's like, it's Friday. What do you mean it's Friday? Friday, 11 o'clock. I don't want to take care of these alerts. The whole infrastructure went down. They've never been able to kind of restore anything, and they ran out of business last year. But that was for me what was insane somehow, right? The hacker took the time to figure out what were the backup systems, went and validated the release version of the backup system to figure out how to do kind of removal of every single backups, then move to the DC. And what was common in the attack, which is most of the attack, is some sort of RPC commands. We started to see kind of these ransomware groups saying, well, I'm going to put some kind of payloads into my kind of remote machines, servers and clients and so on, and then do RPC call to trigger them. So that's kind of the technique we see. So there are many things that have evolved. Before it was if you think about the WannaCry type of malware, which is you replicate your payload across multiple systems that are potentially vulnerable. Right now it's you've got an open file share, you push your payload, you abuse RPC to start the payload for remote, and then nobody sees anything. It bypasses most of the IPS prevention systems, it bypasses most of the IDS prevention, because it's a unique payload, because it's just a file that you transfer across the network, because that file looks like a Word file, because they got some very good evasion techniques around, and it just doesn't look like an executable file, and then with RPC that perform this run. That is the biggest change that I see right now.
Thank you, Gregory. That was really exhaustive, and you answered actually 2 my additional questions that I have. Any other questions from the audience we have? If we don't have any other questions from the audience, I thank you so much for now, and we will meet us at 2 p.m. in the executive track. There will be one presentation, and after that presentation we will meet again here. For those who are interested in a technical track, there will be another presentation here, so feel free to join us and enjoy the lunch. Thank you.
Thank you,
Gregory.